Okay, we will continue our discussion on Fourier series. So, in the last class we left at the point where we just defined what is known as an odd function and what is an even function. So, there are some simplifications if a function is odd, there are some simplifications if the function is even. Okay. The simplification is in the computation of the coefficients, the Fourier coefficients A h or B h. Of course, we can do the other way where we compute the coefficient C h also. So, the simplification is mainly in terms of finding the integral over a certain duration. So, it can be in the form of reduced duration for which we integrate, or we already know that for some cases either A h or B h is 0. So, thereby there is a simplification. Okay. So, our intention is to compute either the fundamental component or the harmonic component using Fourier series. Of course, though average is something which is given by Fourier series, I mean one need not get into the get into Fourier series to get the average, because average is something which is more basic than Fourier series. Okay. So, let us consider some special cases where there is some symmetry. If f of omega o t is an odd function. So, a function is said to be odd if f of minus omega o t is equal to minus f of omega o t. So, in this case I will not get into the derivations. See, if you are not familiar with these results, I would suggest that you verify this. Okay. So, I am not sure whether you have heard of Fourier, odd function, even function in the context of Fourier series. So, what is simplification in the case of odd function? If at all you recall, A h is 0, A h is 0 in the case of odd function. So, one has to find only B h, and there is a further simplification in the computation of B h. So, one need not integrate over the full cycle of 2 pi radian. So, the simplification is one has to integrate only for a duration of pi radian. So, it is 2 by pi integral 0 to pi f of omega o t sin h omega o t d omega o t. So, this is the simplification for B h. So, you will see that for all values of B h. So, h takes all values from 1, 2, 3 and so on up to infinity. So, there is only B h, and that too the integration is only over half a cycle, that is for 180 degrees. If on the other hand f of omega o t is an even function, so a function is said to be even if the function evaluated at the negative of an argument is same as the function evaluated at the value of the argument. Okay. So, if f of minus omega o t is f of omega o t, then we say that the function f of omega o t is an even function. So, in this case B h is 0 and A h has an expression which is simpler than the original expression. So, again the integration is only for pi radians. So, it is 2 by pi integral 0 to pi f of omega o t cos h omega o t d omega o t, and B h is 0. There are other types of symmetries, for example, half wave symmetry, quarter wave symmetry. So, let me define half wave symmetry. If f of omega o t possesses half wave symmetry, So, the term half wave actually indicates that the entire information is contained in half a cycle. So, please note when we talk about periodic functions, the entire information about the function is actually there in just one cycle. So, if I know one cycle, I know the function itself. So, in the case of half wave symmetry, there is a further reduction from 2 pi radians to pi radians. So, the entire information is contained in only 180 degrees or pi radians. So, what is the definition? The definition of half wave symmetry is, when we say that f of omega o t has half wave symmetry, if f of omega o t plus pi is equal to, if at all you recall, minus f of omega o t. So, if that is true, then we say that f of omega o t has half wave symmetry. Now, in this case there is a simplification. What is simplification in this case? Do you recall? Do you recall the simplification in this case? Only odd harmonics. So, for all even values of h, a h as well as b h is 0. So, let us look at the expression a h. So, a h is 0 when h is equal to, what about 0? If h is 0, then a h is 0. Say h is 0 means it is an average value. Average is 0 for half wave symmetry. So, 0, 2, 4, 6, so on. So, for all these values of h, a h is 0, and for h equal to 1, 3, 5, so on, we have an expression, but what is the simplification? We do not integrate over again one full cycle, half a cycle. So, it is 2 by pi integral from any arbitrary constant c to c plus pi f of omega o t cos h omega o t d omega o t. So, this is the expression for h equal to 1, 3, 5, so on. Now, when it comes to b h, again b h is 0 for h equal to, b h is not defined for h equal to 0, 2, 4, 6, so on. So, again for all the even values of h, b h is 0, and for odd values of h, it is 2 by pi integral any arbitrary constant c to c plus pi f of omega o t sine of h omega o t d omega o t. So, this is applicable for h equal to 1, 3, 5, so on. So, we see that only odd harmonics are present if there is half wave symmetry. Now, there is a further simplification possible if the function possesses what is known as quarter wave symmetry. Now, before going to a general definition of quarter wave symmetry, we will take some special cases. Suppose I have combination of odd and half wave symmetry or even and half wave symmetry, then what happens? Okay. So, if f of omega o t is an odd function and also has half wave symmetry then in this case what is a h? So, we know that for odd function a h is 0, okay. And what about b h? So, if you look at b h, again b h is 0 for, since it has half wave symmetry, for even values of h, b h is 0. So, I get two expressions for b h. it is 0 if h is equal to 2, 4, 6, so on. And when it comes to the odd values of h, then there is a further reduction in the duration for which we integrate. So, we do not integrate over, I mean one need not integrate over pi radians, we can just integrate over quarter cycle, that is pi by 2 radian. So, in this case the expression will be, please note I am not deriving any of this. If you are not familiar with these results, please verify these results. It is 4 by pi integral 0 to pi by 2 f of omega o t sin h omega o t d omega o t. So, this expression is applicable if h is equal to 1, 3, 5, so on. So, what is to be noted is, whenever there is an odd function which has half wave symmetry, there is no AH, and of course, BH is 0 for even values of h, and for odd values of h, BH is obtained by integration over quarter cycle. Okay. Now, let me take one more combination. If f of omega o t is an even function, and has half wave symmetry, now in this case, since it is even, BH is 0, and when it comes to AH, again AH is also 0 for certain values of h, that is even values of h. So, AH has two expressions, one is 0 when it comes to h equal to 0, 2, 4, 6, so on, and for odd values of h, it is 4 by pi integral 0 to pi by 2 f of omega o t cos h omega o t d omega o t for h equal to 1, 3, 5, so on, and for all values of h, BH is 0. Now, instead of saying odd function and half wave symmetry, we have we have just a name for a function which satisfies both the property of odd function as well as half wave symmetry. What is that, if you have heard of that? Say, actually the hint is in the expression. If you look at the BH expression in the case of odd function half wave symmetry, it is integration only over quarter cycle. Similarly, even in the case of even function and half wave symmetry, in the expression for AH for odd values of h, the integration is only over quarter cycle. So, in fact, the information is contained in quarter cycle. So, we say that this particular function, either the case of odd and half wave symmetry or even and half wave symmetry, is as good as saying quarter wave symmetry. So, we say that, I will just write it here itself, then it has what is known as quarter wave symmetry. So, even in the other case, if f of omega o t is an even function and has half wave symmetry, then it is said to have quarter wave symmetry. But these are only two special cases of quarter wave symmetry. So, what is the definition of quarter wave symmetry? Say, quarter wave symmetry means the entire information is contained in quarter cycle, but these are only two special cases. There are other possibilities where the function need not be even or odd. So, even if the function is neither odd nor even, it can still have quarter wave symmetry. Okay. So, that is still possible. So, we can have a very general definition of quarter wave symmetry. These are just special cases. So, what I will do is I will try to give the definition. Let us see whether it makes sense. F of omega o t is said to possess quarter wave symmetry. So, quarter wave symmetry is of course a special case of half wave symmetry. See, please note that in the previous two special cases, as in both cases I have said half wave symmetry, but in one case it is odd, another case is even. But the point I am trying to make is a quarter wave symmetry waveform can neither be odd nor be even, but still have quarter wave symmetry. But invariably it will have half wave symmetry. Okay. So, by definition, f of omega ot is said to possess quarter wave symmetry if it has half wave symmetry and I put one more condition so that it has quarter wave symmetry in addition to half wave symmetry, and there exists a phi is some real number, there exists a phi such that so what I am trying to do is I am trying to give a definition which is very general for quarter wave symmetry. So, the definition is like this, such that f of omega ot plus phi is equal to what? See, what I am trying to do is I am trying to shift the waveform of f of omega ot. See, by shifting a waveform, the harmonic component, the RMS value of any harmonic component or fundamental or DC does not change. See, by shifting to the right or left, say only by shifting vertically you will have a change in the values, but by shifting laterally to the right or left, say when I change the argument from omega ot to omega ot plus phi, I am essentially not changing the value of any harmonic component or fundamental or average value. Okay. So, what I am trying to do is I am shifting in such a way that I am shifting the axis, say there is a omega ot equal to 0 axis, which is the vertical axis. See, our independent variable is omega ot. So, omega ot equal to 0 is the vertical axis. So, I am just shifting the position of the vertical axis such that this function becomes an even function, that is all I am trying to do. Okay. So, if I want to make it an even function, I should say that f of omega ot plus phi is equal to f of minus omega ot plus phi. Is that okay? So, there should exist such a phi, so that if I shift either to the right or left depending on whether phi is positive or negative. Okay. So, I should be able to shift it to the right or left such that I get an even function if I change the omega ot equal to 0 axis, that is all I am trying to say. Of course, it should always have half wave symmetry. So, half wave symmetry and even function, of course, we just now saw that it has quarter wave symmetry. Okay. So, this is the very general definition of quarter wave symmetry. So, in general f of omega ot need not be even or odd, but still it can have quarter wave symmetry. Okay. So, that is the definition of quarter wave symmetry. So, if a function has quarter wave symmetry, then what is the expression for AH and BH? So, if f of omega ot has quarter wave symmetry, then what is AH and what is BH? Of course, one of them is easy. One of them is easy to say. Easy means one of them is 0. Which one? Say yeah, because I am trying to find a phi so that it will shift the omega ot equal to 0 axis in order to make it an even function. See, I am not putting a minus here. F of omega ot plus phi is equal to plus f of minus omega ot plus phi. So, BH is 0. Now, when it comes to AH, I need to again consider two sets of values. So, for some values it is 0, of course, it has half wave symmetry. So, it is 0 for h equal to 0, 2, 4, 6, so on. Okay. For h equal to 1, 3, 5, again there will be a simplification. The simplification is that I have to integrate over only quarter cycle. So, it is 4 by pi integral 0 to pi by 2 integral of what?
Integral of this function f of omega
Yeah.
t plus phi.
So, it is not integral of f of omega o t, it is integral of f of omega o t plus phi. Now, please note I am trying to find an harmonic component of a waveform which is shifted to the right or left depending on whether phi is positive or negative. Now, that does not alter the RMS value, that is the point. Okay. Please note RMS value is not altered by shifting a waveform to the right or to the left. Cos h omega o t d omega o t. So, this is applicable for h is equal to 1, 3, 5, so on. So, the point to be noted here is RMS value of fundamental component or harmonic component, fundamental or harmonic component of f of omega o t plus phi is same as that of f of omega o t. So, there is one set of harmonics which are very important in the AC system, that too in the 3-phase AC system, that is the third harmonic, sixth harmonic, ninth harmonic, 12th and so on. So, what I am talking about is the multiple of 3 harmonics. So, these are known as, there is a name for this, triplen harmonics. So, triplen harmonics play an important role in power systems which are 3-phase systems. So, triplen harmonics, these are harmonic components of order 3 or its multiples. Now, if I take 3-phase waveforms, either voltage or current, so I will use a general notation F. So, if they are balanced, so please note what I am talking, I mean, when I say balance, what I mean is not a sinusoidal unbalance. Suppose the currents or voltages in the 3 phases are identical except for a phase shift of 120 degrees. So, suppose I take a function f of omega o t as a current waveform or voltage waveform in phase A, then the current waveform or voltage waveform in phase C, phase B is just f of omega o t shifted by 2 pi. Then in phase C it is again f of omega o t minus 2 pi by 3 with a further phase shift. Now, please note I am talking about quantities which are not sinusoidal. If it is sinusoidal, then obviously we do not need any harmonic Fourier series at all. So, there are harmonic components in either current or voltage. So, instead of using notation I or V, I am using F. Okay. So, if I look at the 3 phases, suppose the 3 phases have an identical waveform for current or voltage except for a phase shift of 2 pi by 3, then what can we say about the triplen harmonic components of these? They are no phase shift. So, if I take the triplen harmonic component of f of omega o t and triplen harmonic component of f of omega o t minus 2 pi by 3, they are identical. There is no phase shift as well. Okay. And that is also identical to the triplen harmonic component of f of omega o t plus 2 pi by 3. Any triplen harmonic component, third, sixth, ninth, so on. Okay. So, for these three waveforms, triplen harmonic components, any triplen harmonic component are equal. So, what I will do is, I will take triplen harmonic component of the first waveform f of omega o t. So, can I write this as, since they are equal, if I take sum of these three waveforms, the triplen harmonic component will be 3 times that found in the individual waveform. So, can I say it is equal to 1 by 3 into triplen harmonic component of f of omega o t plus f of omega o t minus 2 pi by 3 plus f of omega o t plus 2 pi by 3. How does this hold? This is because, say, if I take any harmonic component, we are just doing integration. Okay. So, if I add two waveforms, then the harmonic component is sum of the individual harmonics, because it is just integration. We know the rules of integration. So, and another fact is that triplen harmonic components are equal for all this. So, this relation holds. Now, what is the inference? What can we infer from this equation? Something which we are very familiar with in case of 3 phase. What do we infer from this? Can we say something about triplen harmonic component from this equation? See, what is the usual value of f of omega o t plus f of omega o t minus 2 pi by 3 plus f of omega o t plus 2 pi by 3? It is 0. Normally it is 0. Under very rare conditions of fault, unbalanced fault, we have non-zero. Okay. So, if f of omega o t plus f of omega o t minus 2 pi by 3 plus f of omega o t plus 2 pi by 3 is equal to 0, which is true normally, okay, then triplen harmonic components are 0. So, just now we saw that there is a possibility of one set of harmonics being 0, that is even harmonics being 0 whenever there is half wave symmetry. Now, we saw that in addition to half wave symmetry, if we have the 3 waveforms, because please note we are considering only on the AC side 3 phase waveforms. Okay. On the DC side, of course, there is only one voltage or one current. On the AC side, we have 3 phase voltages, 3 phase currents. So, if the current or voltage on the AC side satisfies this equation, that means f of omega o t plus f of omega o t minus 2 pi by 3 plus f of omega o t plus 2 pi by 3 equal to 0, then the triplen harmonic components are 0, in addition to the even harmonics being 0 if at all there is a half wave symmetry. Okay. So, this way we will note that there are many possible harmonics which are just 0, we need not even try to apply Fourier series to note this. Okay. Now, before going back to the topic, I will just define one more quantity, total harmonic distortion. Is usually abbreviated as THD. So, suppose I use this notation F. So, instead of using I or V for voltage or current, I am just using a general notation F, so that it is applicable for voltage or current. Suppose F is the RMS value of our periodic waveform f of omega o t, okay, and F1 is the F subscript 1 is the RMS value of fundamental component of f of omega o t. then THD is just defined as a ratio. So, what is the definition of THD? Are you familiar with THD, total harmonic distortion? It's a root of f square minus f1 square divided by f1. So, I will not try to get into other possible definitions. There are other equivalent definitions for this. So, this is the one which we are using. If at all we, this is the easiest one to use. Instead of there is another definition which starts with a summation. So, that is a series in fact. Okay, that of course is rarely useful. If I want to use the expression for actually computing the value of THD, if I have f and f1, I can easily find out. Okay. Sometimes you multiply it by 100 and say that THD is in percentage. Okay. So, this is about the Fourier series, which will be useful for finding the harmonic components. So, if any of the results that were mentioned in this class is not known to you, I would suggest you derive it.